Welcome, I'm Dominic, and this is perhaps the first in maybe a series of videos on the adventures of repairing this Tektronix 2465A DV oscilloscope. I've had it for decades now. It's worked great. So on the chassis it states 1987. This is this broke down in February 2026. It's worked well until then. It seems there's been a RIFA blowout, which is fairly well known. So this 350 megahertz oscilloscope also has, and it's indicated by the name DV, a digital multimeter, and that's all those buttons and plugs on the top of the scope there. That's for the digital multimeter functions. And the this particular series, it is the one with the Siemens Hall effect DC brushless motor with the impeller blade that blows the air out, which is an important detail about finding the correct service manual. So further on in the video I'll get into some details about what happened to this thing and the repairs that were done and where this project is heading. Welcome again. So this slide is just here to document in black and white the salient features of this repair project and the reasoning to repair. This is just that I've had this scope for decades. Tektronix scopes are great. The through-hole design is easy to repair, I think. The documentation is out there for all the components that I might need to replace. So there's multiple reasons why it's convenient to just fix this thing and keep using it. But I'm not arguing against digital, no. Anyway, the background of this incident, findings, actions are listed here. I would just say that I'm in Sweden. So we have 240 volts. We can have voltage excursions over 250. So the X2 and Y2 type caps, these were replaced with 275 or 300 volt types. The various actions I took here resulted in the scope now turning on. So some electronics learning is going on around here. But after the diagnostic test, and I'd say about 5 to 10 minutes after the power is turned on, the scope goes into a power wind down. So where things stand today is it seems there may be some components that are experiencing some form of thermal stress or something like that. I've actually used a thermometer to check different parts of the A2 and A3 boards. I don't find any particularly high temperatures, nothing above about 31, 32 degrees C. So it is possible there's a component that as it warms up is failing. That'll be for later discussion, but that's the current situation. The next slide I'm going to get into the schematic and details about these components. So first thing to do is to hunt down the correct service manual. Now it does exist on archive.org, but archive.org is a bit tricky with the search engine there. The secret to finding this particular service manual, and again this is the one with the Siemens blower fan with the impeller blade, is to just type in 2465 SVC and you will come directly to this manual, which is the one that actually has that unusual Siemens blower fan. So if you have that, this is the match for that particular scope, I think. I would point out that if you look specifically for the file that ends in text.pdf, the text version, that file is searchable. Many of the other manuals are just basically images where you can't search them, but this particular one is searchable. So if you type in C1018, you get to replacement part list and so on. So much more handy to have that. I can also mention that if you in archive.org, if you type in 2465 fan collet, that will take you to information for needed for 3D printing of that fan collet that seems to always break when people try to open up take out the impeller to get at the voltage regulator and inverter boards So that's the important detail. The you can see in this schematic here, which is on page 260. All of this is on page 260. The other information about the power supply, it's in the pages before and after this. So this is the region of the manual where you want to be. So the C1018, you can see here, I use the sun symbols where I mark the things I've replaced. So the C1018, you can see here, that's the one that blew out, and below it, the R1018, that was badly damaged. It burned underneath on the circuit board, and so both of these were replaced. C1016 here, that was still intact, cracked but intact. So I took it out and measured it, and it measured 0.09. Now, if you look at replacement parts lists, you can see that they list the original condenser as 0.068, but the replacement is 0.1. Well, that's kind of important detail if you're worried about things like inrush currents. I don't know what to make of this, but later manuals for some of these scopes, they did actually have a 0.1 here. So I'm not sure if that's a later revision, but anyway, this C1016, it measured at 0.09. So I took out some 0.1 microfarad X2 caps, and I looked for some that were the lowest of that bunch, and so I found a couple that were 0.09, which is pretty close match to what this had in it the last time it was working, which was 10 February 2026. So any measurements I might discuss here, it says as of 2026. So you can see here the Y2 caps in the middle here, the C1020 and the C1051. They're both 2200 picofarad Y2s, and you can see they're both grounded as expected. The C1052 is a 0.01 microfarad, and I think it's an X-type condenser that was replaced. So all of these 5 RIFA caps, they were badly cracked, and I would mention that capacitance values in all of these, at least the ones that were still intact, 4 of them, they were actually pretty close to what I think were the specification values, or the original values. But compared to the new capacitors that I put in, the difference is in the leakage current. I measured that by measuring across a 1 mega ohm resistor in series with each of these condensers. And so I had the multimeter in the millivolt setting, and then 1 millivolt will be 1 nanoamp with that 1 mega ohm resistor, and that's how I measured leakage. So whether it's calibrated or not calibrated, what I know for sure is all of these had leakage currents that were a lot higher than the new ones they were replaced with. So I don't know if that means old caps had more leakage and new ones have less, or if this was evidence of caps that really need to be replaced. But the cracks were clearly, to me, good enough reason to replace them, and they're gone. It's expert opinions all over the place about replacing RIFAs. Okay, so on that same page 260, I'll point to just one little excerpt from the right side of that schematic, which is about the fan. I would point to the fact that on that J301 junction, you'll see this plus 19.2 volts here in a circle. Well, that's where it's specified as plus 15 volt unregulated. If you measure at that junction with a 24 volt fan connected to it, where I think that in my case it's a power draw that's similar to the original Siemens fan, what I measure is 19.2 volts. So I don't think this is an overvoltage. I think that this section is producing exactly the voltage it's supposed to, and what's coming out at that junction is 19.2 volts. If you attempt to put a 12 volt fan on there, you might notice it blowing very, very hard, and I have a feeling you're just going to destroy that fan. So I put in a 24 volt fan, and that seems to be just fine for now. So little detail. You see here the C1112 4.7 microfarad electrolytic cap that was leaking all over the A3 board around it, and so that was replaced. So this is basically everything I changed on this thing in So I think I'll stop this slide here. So here I'm showing the actual hardware, some of the highlights of the repair thus far. So A is the A2 low voltage power supply board, and in B is the A3 inverter board. These two boards normally they're sandwiched together. So on the A2 board, these blue rectangular caps, these are the X2s. So the lower one, that's C1018, and next to it is the R1018 that's in series with that cap that's been replaced. So the black object here to the left of the board, that's the 115-230 volt selector switch, and that had black powder all over the bottom of it that was I suspect conductive material that came from the resistor and the condenser when it blew, and so that required a lot of cleaning, and that could have easily been missed. So I'm kind of mentioning that because you have to think about consequences when these components break, that there's surrounding components that can be dirty that are maybe not even obvious. Anyway, that was a little detail there. It's kind of important. On the B board, I'm sorry, the A3 inverter board in figure B here, panel B. Let's see. We'll start on the left side here. The lower side here, this is the C1112 electrolytic that's been replaced, and there was fluid all over here that had to be cleaned. Now there's a bunch of diodes in here. I've tested all of them. They all consistently keep testing fine. Down here is the C1051 Y2 cap, and this blue over here, this is the new C1052 10 nanofarad X cap, and over here is the other Y2 cap, and that's the C1020 where the eyelets came out during desoldering. Just above that there is the S10 thermal cutoff switch. So in C and D, I'm going to zoom in on that. So this is the back side of the C1020, and you can see my wire wrap job. The eyelets are missing on both the holes. So this is just transformer wire that I've sanded to remove the insulation, and that's up above here. There's a leg from another condenser. What I'm doing here is like trying to shore up this connection between these 2 points because it looks a bit damaged. So on the right side of this panel C here, you can see what that hole looks like prior to the wire wrap repair. So all this has now been soldered up. I've checked for connections and things, and it seems pretty secure. In D, this is the other side of the board where you see the component side of the board. The cap, Y2 cap, C1020, it now seems pretty secure. But right above it, that's the S10 thermal cutoff switch, and that component is now becoming a little bit suspect. The observation after all these repairs is that after I turn on the scope, it gets through the diagnostics, and then somewhere around 5 to 10 minutes, it powers off. So it seems like the scope is experiencing some kind of issue where as it warms up, there's a component that starts to fail. So this is among the components on the list that needs to be checked. Now, when the scope is cold, turned off, and these things are pulled out of the scope, they're testing normally. But it seems that once it warms up, something in here is no longer normal. So I'm thinking what I may do is pull this board out and put it into an oven at about maybe 50 degrees and see how it and other components work when they're actually warm. So I can mention again that the I had a thermometer in the scope when it was turned on, and I tried checking the temperature along the A2, A3 board, and I couldn't find anything above 31, possibly 32 degrees C. So whatever this failure is, it's not needing to get to even, I think, 60 degrees. So something seems like it's failing as it warms up. So as of today, this scope turns on. It looks like it's going to work fine, but I've got a power wind down issue I need to trace down, and who knows, maybe it'll last another 40 years. I don't really know. So thanks. I'd like to acknowledge some people in YouTube and Facebook. There's a bunch, but EEV blog, Kiss Analog, Tech Tom, W2 AEW, the Tech Genie, Zen Wizard Studios, and IMSE Guy. There are many others, but thanks all of you. Your videos were in some way helpful. And then in Facebook, there's Old Tech Scopes. Have a look there as well. There's a lot of brilliant people. Okay.